Imagine holding a piece of paper. Point A is on one corner, point B is on the opposite corner. The shortest distance between them is a straight line across the paper. But what if you folded the paper in half? Suddenly, those 2 points touch. The distance becomes 0. Now replace that paper with the fabric of spacetime itself. Replace those points with moments in time, say, this morning and next Tuesday. What if time could fold the same way? This isn't just science fiction fantasy. The mathematics of general relativity, Einstein's masterwork that revolutionized our understanding of reality, doesn't actually forbid time from folding. In fact, the equations suggest it might be possible under extreme conditions. Today, we're exploring what would happen if time could genuinely fold, bringing distant moments together like creases in fabric. The science is real, the implications are mind-bending, and the consequences would reshape everything we know about cause, effect, and existence itself. Let's fold time. To understand how time could fold, we first need to understand what time actually is. For most of human history, we thought of time as absolute, a universal clock ticking the same for everyone, everywhere. Then in 1905, Albert Einstein shattered that assumption with special relativity. He showed that time is relative. It flows differently depending on how fast you're moving. But Einstein went further. In 1915, his general theory of relativity revealed something even stranger. Space and time aren't separate things. They're woven together into a single four-dimensional fabric called spacetime. And this fabric isn't rigid. It bends, warps, and curves. Massive objects like planets and stars create dips in spacetime, like a bowling ball on a trampoline. This curvature is what we experience as gravity. When you fall, you're not being pulled by a force. You're sliding along a curve in spacetime itself. Here's the key insight. If spacetime can curve, if it can bend and warp, then mathematically, it should be able to fold. The equations don't distinguish between gentle curves and sharp creases. Princeton physicist John Wheeler, who coined the term black hole, explored scenarios where spacetime could develop extreme geometries. In standard physics, we visualize time as moving forward along a timeline. But in general relativity, that timeline exists in a higher dimensional space. And in higher dimensions, folding becomes geometrically possible. Physicists use something called a Minkowski diagram to map spacetime. Your position in space is one axis, your position in time is another. Your path through life traces a line called your world line. Now, if spacetime could fold, different parts of that world line could potentially touch, bringing different moments into contact. This is where it gets wild. So what would it actually take to fold time? According to our best understanding of physics, you'd need extreme spacetime curvature. We're talking about conditions that make black holes look gentle by comparison. Let's explore the candidates. First, rotating black holes. In 1963, mathematician Roy Kerr discovered that rotating black holes create something called frame dragging. They literally twist spacetime around them like a whirlpool. Inside the ergosphere, the region just outside the event horizon, spacetime is twisted so severely that certain paths could theoretically loop back on themselves. The Kerr metric equations suggest the existence of closed time-like curves, paths through spacetime that loop back to their starting point in time. If you followed such a curve, you'd return to your own past. That's not quite the same as folding time, but it demonstrates that the mathematics of general relativity allows for bizarre temporal geometries. Then there's the concept of wormholes. Einstein and physicist Nathan Rosen proposed in 1935 that general relativity permits tunnels through spacetime connecting distant points. These Einstein-Rosen bridges could theoretically connect not just distant places, but distant times. Physicist Kip Thorne from Caltech, whose work on black holes won him the Nobel Prize, explored whether wormholes could be traversable. His calculations showed that you'd need exotic matter, material with negative energy density, to keep the wormhole open. This stuff has never been observed, but quantum field theory suggests it might exist in microscopic amounts through something called the Casimir effect. For time to truly fold, bringing different moments together across a boundary, you'd likely need a combination: rotating supermassive black holes, exotic matter, and energy densities beyond anything we can currently produce. We're talking about civilizations at least Type 2 on the Kardashev scale, capable of harnessing the energy of entire stars. But let's say it's possible. Let's say somewhere, somehow, time folds. What happens next? The moment time folds, the most fundamental law of our universe, causality, the rule that effects must follow causes, shatters. Imagine a fold brings Tuesday morning into contact with Monday evening. Information, energy, or matter could cross that fold. You could receive a message from your future self. You could observe events before they happen. The very concept of before and after loses meaning at the fold point. Philosophers and physicists have debated paradoxes like this for decades. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you're never born. But if you're never born, you can't travel back. It's a logical impossibility. Oxford physicist David Deutsch proposed a solution using quantum mechanics. His theory suggests the universe splits into parallel timelines. When you change the past, you create a new branch of reality. Your original timeline remains intact, but you're now in a different version where your actions have altered history. This is called the many worlds interpretation, and it has serious scientific support. Nobel laureate Frank Wilczek and others have shown it's mathematically consistent with quantum field theory. But there's another possibility, one that's darker: the Novikov self-consistency principle proposed by Russian physicist Igor Novikov. This principle states that the universe will actively prevent paradoxes. If time folds and creates the possibility of changing the past, events will conspire to make those changes impossible. Try to stop your grandfather from meeting your grandmother. You'll slip on a banana peel. Your gun will jam. The universe itself will bend probability to maintain consistency. It sounds supernatural, but Novikov showed it follows from the mathematics of general relativity. Research published in Classical and Quantum Gravity has explored these scenarios mathematically. The consensus is strange. Time folding doesn't break physics, but it forces physics to behave in extremely counterintuitive ways to maintain logical consistency. Now here's what most people don't consider. Causality breaking down isn't just about time travel paradoxes. It affects everything. If time could fold routinely, if it became a common phenomenon rather than a theoretical extreme, reality itself would become fundamentally unstable. Consider entropy, the second law of thermodynamics, which states that disorder always increases over time. This law is why eggs break but don't unbreak, why coffee cools down but doesn't spontaneously heat up, why we age instead of growing younger. Entropy defines time's arrow. But if time folds, entropy loses its meaning. At the fold point, future high entropy states could contact past low entropy states. Broken eggs could influence their unbroken past. The arrow of time would become circular, or worse, completely tangled. Physicist Sean Carroll from Johns Hopkins has written extensively about this. In his book, From Eternity to Here, he explains that our entire experience of past, present, and future depends on entropy increasing in a consistent direction. Fold time, and that consistency evaporates. Memory itself would become impossible. Your memories exist because your brain is a recording device moving forward through time, accumulating information. But if time folds, the future could imprint memories of events that haven't happened yet. You'd remember things in the wrong order, or remember multiple contradictory versions of the same event. The psychological impact would be devastating. Human consciousness depends on narrative, the story of our lives unfolding sequentially. Research in cognitive neuroscience shows that people who lose the ability to form sequential memories, like patients with severe amnesia, struggle to maintain a coherent sense of self. Now imagine an entire civilization experiencing that. You'd wake up remembering both going to work and staying home. You'd know tomorrow's lottery numbers, but also remember losing the lottery. Every decision becomes meaningless because you simultaneously experience all possible outcomes. Some physicists speculate this is why we don't observe time folding, even though the equations allow it. Perhaps universes where time folds become so chaotic, so unstable, that they collapse or fail to develop complex structures like stars, planets, and life. We exist in a universe with stable time because only stable time universes can produce observers. This is a form of the anthropic principle, the idea that the universe appears fine-tuned for life because only fine-tuned universes produce beings capable of asking the question. But let's think more optimistically. What if an advanced civilization learned to control time folding? What could they accomplish? First, instantaneous information transfer. Quantum entanglement already allows particles to share states faster than light, but you can't use it to send messages. Time folding would be different. You could fold time to bring two moments together and transfer information across the fold. Communication would be instantaneous across any time span. This would revolutionize everything. Imagine historians directly accessing primary sources from ancient Rome. Scientists could observe the formation of the solar system in real time. We could witness the Big Bang itself, testing our cosmological theories with direct observation. A 2017 paper in Physical Review D explored whether information from folded time could violate the second law of thermodynamics. The authors concluded that while you could transfer information, extracting useful work from it would still be bounded by thermodynamic limits. You can't create a perpetual motion machine, even with time folding. There's also the possibility of accelerated evolution and learning. A civilization could fold time to create isolated pockets where thousands of years pass in subjective time, while only moments pass outside. You could develop technologies, run experiments, evolve cultures, then return to share the results. This is similar to time dilation near black holes, which we know is real. GPS satellites have to account for relativistic time differences, but time folding would be far more extreme and controllable. However, weaponizing folded time would be terrifying. Imagine folding time to retroactively change the outcome of a war, or bringing future doomsday weapons into the present. The strategic implications are nightmarish. Any civilization with time-folding technology would have essentially unlimited power over all other civilizations across all of history. This leads to a disturbing thought. If time folding is possible, and if advanced civilizations eventually develop the technology, why haven't we been contacted by time-folding beings from the future? Maybe we have been, and the universe's self-consistency mechanisms prevent us from recognizing it. Or maybe civilizations that develop time-folding technology inevitably destroy themselves in temporal paradoxes. Or maybe, and this is the hopeful option, they're watching carefully, waiting for us to reach a level of wisdom sufficient to handle such power. Time folding remains theoretical. We've never observed it. We have no technology to create it. But the mathematics says it's not impossible, just incredibly difficult. What this thought experiment really reveals is how strange our universe actually is at its foundations. Time isn't the simple flowing river we experience in daily life. It's a dimension of space-time that can bend, stretch, and potentially fold. General relativity has been tested thousands of times and never failed. It predicted black holes decades before we found them. It predicted gravitational waves a century before we detected them. So when its equations suggest time folding is possible, we should take that seriously. Perhaps the real question isn't, What if time could fold? But under what conditions does it already fold in extreme regions of the universe we haven't explored yet? Rotating black holes, cosmic strings, the Big Bang itself. These are environments where space-time behaves in ways we're still struggling to understand. Maybe time folding happens naturally in these extremes, waiting to be discovered. The universe has surprised us before. It was bigger than we thought, older than we imagined, stranger than we dreamed. Each time we push the boundaries of knowledge, reality turns out to be weirder and more wonderful than our previous conceptions allowed. So maybe somewhere in the heart of a supermassive black hole, or at the edge of the observable universe, time is folding right now. Different moments touching across the fabric of space-time, past and future becoming neighbors. The timeline not a line at all, but an origami sculpture of infinite complexity. And maybe one day, we'll learn to fold it ourselves. Thanks for watching. If this journey through the mathematics of time bent your brain in interesting ways, hit that like button and subscribe for more explorations of the universe's deepest mysteries. Until next time, or perhaps until last time, keep imagining.